SED Technology has recently won a 20-month grant to continue research on the use of infrared technology and potentially improve the accuracy of the NIBIN system. The current grant includes 3 major subtasks. These include: determine the persistency of firing pin impressions that can only be seen in infrared. Show the ability to accurately match both pristine and deformed bullet siblings using infrared technology. Demonstrate the ability to image, store, and accurately identify sibling cartridge cases from a large database of infrared images. This capability is possible considering the history of firearm forensics and the world-class infrared knowledge of SED personnel. This background is shown in the following segments.
The basis for firearms identification is the fact that when firearms are manufactured, very hard steel tools such as this rifling broach are used to form and shape the metal into what we recognize as a firearm. An example would be, in the case of this pistol, we would be talking about the breech face, the firing pin, the extractor, the ejector, or the interior of the barrel. These very hard steel tools leave unique and reproducible microscopic marks on these operating surfaces of the firearm. And these marks are also transferred to the surfaces of fired ammunition components such as this cartridge case or this bullet. Now these marks can be reproduced by simply firing a seized firearm to obtain known specimens of fired bullets and cartridge cases from that gun, and on the basis of these unique and reproducible marks, a bullet and a cartridge case can be identified as having been fired from a particular firearm to the exclusion of all others. The essential tool of the trade for a firearms examiner is something called a comparison microscope. The comparison microscope dates from 1925, and it is essentially just 2 compound microscopes joined by something called an optical bridge, which allows the examiner today to look through binocular eyepieces and see 2 specimens at once, optically side by side. Now these cartridge cases, as they work through the action of a firearm and are fired, do also pick up marks on the ends of the cartridge cases from a firing pin or from the breech face, so-called, that supports the base of the cartridge case during firing. These 2 also can be mounted on a comparison microscope, where they are in fact physically separated but optically next to each other, and the examiner can observe these through a binocular eyepiece. And again, if there are sufficient similarities, the examiner can say, yes, these were fired in the same weapon to the exclusion of all others. With the widespread use of the comparison microscope, it became very common for police agencies to accept large numbers of firearms cases for examination. The result was the accumulation of many known specimens as far as previous cases. The question, logically, would be on today's case, today's received evidence, is it related to any of the previous cases of the same caliber? This was easy to do early on when only a few dozen or a few hundred cases existed in storage. But as cases accumulated in their thousands, it became completely impractical to do, unless there were some informant information or some investigative information that indicated that today's case needed to be, it was logical to compare today's case against previous cases submitted by the police agencies. By the end of the 1980s, something better had to be done. And by that point, something better could be done. New technologies were developed that allowed the creation of images of the microscopic marks on fired bullets and fired cartridge cases. Along with that were the enhanced storage capacities for the image type data, along with the ability to manipulate the data and to compare the image data using pattern matching algorithms. Inevitably, competing systems developed and evolved to compare this image type data. They all encompassed certain factors: some kind of image capture, some way of comparing the patterns in the various specimens that were stored, and some way of ranking the probability of association. All of these computer-assisted case linkage systems involved visible light. A common complaint amongst users and examiners who were involved with the system was, and still is, that there are too many false positives or high probability associations generated to be easily handled by an individual examiner. So if some means could be found of refining that number, this would be a goal.
The goal of this task is to determine if firing pin impressions significantly change with multiple firings. To do this, we first obtain a diverse group of firearms as shown. Next, we fired 1,000 rounds through each firearm and collected the cartridge cases. We are now in the process of imaging every 100th and determining the amount of change and how accurately we can continue to match the images. This analysis will be completed by the end of September 2010.
Besides lowering the number of false positives to deal with in the absence of any lighting issues, there are a number of advantages to infrared systems. A continuing problem with visible light case linkage systems has traditionally been the large number of false positive results the systems have generated. A solution to this is the use of infrared imaging as opposed to visible light. The benefit of infrared imaging is that more detail is available, more information is available in the image than under visible light systems. The use of this segment of the electromagnetic spectrum allows for the construction of images with much more detail than are obtainable under visible light. The use of infrared imaging allows us to effectively see in the infrared range and to construct images with far more detail than available in visible light. Using these enhanced images together with enhanced computer algorithms allows us to generate far fewer false positive results. It's interesting that no visible light is necessary for image capture. This eliminates the need for oblique lighting, for ring lights, for lighting protocols. Glare effects are not a concern, and reflectivity of different surfaces on fired ammunition components also not a concern. Besides lowering the number of false positives, there are a number of significant advantages to either integrating an infrared capability with existing systems or maintaining a standalone configuration. The infrastructure of existing systems does not need to be replaced. There is an increased ability to respond to client agencies in regard to possibly linked cases. There is significantly less time spent by examiners in physical intercomparisons. From a management perspective, there's backward compatibility with all existing visible light images of current or legacy systems. In other words, current systems do not have to be archived. Infrared is retrofit capable as far as hardware and software, and it's suitable for complementing existing case linkage systems. There's a potential for local control of databases and related correlations or comparisons. The infrastructure of existing systems does not need to be replaced, and there is the more efficient use of examiner time in case linkages, simply because there are fewer false positives to deal with. At this point, the benefits of infrared imaging applied to firearms case linkage should be very apparent to both lab managers and to bench examiners. This research is continuing. Thank you.